Tensor densities are generalizations of tensors. They also have well-defined transformation rules under diffeomorphisms or general coordinate transformations, so they are objects which are well-defined on differentiable manifolds. The transformation rule for a tensor density can be expressed of weight omega. So they are characterized by a number, a real number, which is called the weight. Is as follows. So for the particular case of a contravariant vector, density of weight omega, the components transform in this way. So this could be the standard transformation rule of a contravariant vector, but then there is an additional factor, which is the determinant of the Jacobian matrix of the transformation raised to the power minus omega. This defines a contravariant vector of weight omega, and this can be generalized to any kind of tensor of ranks Rs, R times contravariant, S times covariant. The only thing that you need to include is an overall factor of the determinant of the Jacobian raised to the power minus omega. The simplest example of a tensor density is the determinant of the metric. In order to show that it really transforms as a tensor density, okay, it will be a scalar density because it has no indices, and we are going to determine the weight. In order to prove that indeed it transforms as a scalar density of weight 2, we start by reminding ourselves how the metric transforms. Remember that according to the general definition, G alpha beta transforms in this way. If I use the notation J mu nu for the Jacobian matrix, here it will be nu, then this transformation rule can be written in this way. It is J minus 1 alpha mu and J minus 1 beta nu. Now, if I want to transform this, to rewrite this in matrix language, I reorder these factors in this way. First I write J minus 1 alpha mu, then G alpha beta, and then J minus 1 beta nu. And then I observe that in the last two terms I am contracting the second index of this matrix with the first index of this matrix. This corresponds to the standard multiplication rule of two matrices. So this will be G multiplied by J minus 1 with three indices alpha and nu that I'm not going to write. Okay, but if I needed to write them, this would be the first and the last index, alpha and nu. However, in the first factor, I am contracting the first index with the first index. Since this is not the standard rule for multiplication, I need to consider the transposed. So this will be J minus 1 transposed times G. Then I am contracting the second index of J minus 1 transposed, which is the first index of J minus 1 with the first index of G, and this is the right multiplication in matrix language. Let me put it in this way: J minus 1 transposed J minus 1. So now, if I consider the determinant, I take the determinant of both sides, then I get that the determinant of G prime is clearly the determinant of J minus 1 transposed times the determinant of G times the determinant of J minus 1. The determinant of the transposed is the same as the determinant of the original matrix, so this is just determinant of J minus 1. I have two factors, so I get this squared, and the determinant of J minus 1 is the inverse of the determinant of J. So this is determinant of j to the minus 2 determinant of g. Okay, and now I compare with the general expression, and then I identify this 2 as the weight. So we can write that the weight of the determinant of the metric is plus 2, and something that it is easier to remember, the square root of the determinant of the metric has weight plus 1, and we will use this very often. We can use this determinant of the metric to convert vectors into vector densities and vice versa. So if we had this this contravariant vector density up here, v mu, you can check that v mu defined as g minus omega divided by 2, and here g is really the determinant of the metric in the standard notation. Okay, here I wrote determinant because I wanted to distinguish between the determinant and the matrix G. Okay, so let me come back here. This v mu, capital V mu, transforms as a vector, as a contravariant vector. So you could say that, okay, I forget about this tensor densities because I can always transform them into standard tensors by multiplying with the right power of the determinant of the metric. Still, it is since the determinant of the metric appears here and there, and then there is another object that also is a tensor density and appears also very often, it is good to study these objects separately, okay, and define certain operations on them. Well, if you sum tensor densities of the same weight, you get another tensor density of the same weight, and you can make linear combinations of them, just as with tensors. When you multiply two tensor densities of two different weights, omega 1 and omega 2, you get another tensor with, well, you sum the ranks, the contravariant number of indices, the covariant number of indices, and you also sum the weights. You get a tensor density whose weight is the sum of the weights of the original densities. Okay. This is more or less what you are doing here. You have a tensor density of weight omega. This is a tensor density of weight minus omega, and you get a tensor density of weight 0, which is a standard tensor. You can also define that covariant derivative on tensor densities, and okay, they are defined in this way. So this would be a scalar density. The first part of this covariant derivative is the standard covariant derivative. In this case, this is equivalent to the partial derivative. And then there is a term which basically takes care of the transformation of this factor, the determinant of the Jacobian, and which is omega minus omega, where omega is the weight of the tensor density, times gamma mu rho rho times f. And this is supposed to be the Levi-Civita connection. And remember the property that the Levi-Civita connection, well, the components of the Levi-Civita connection are the Christoffel symbols, and in particular, okay, mu rho rho. This is nothing but the partial derivative of the log of the square root of the determinant of g. Okay, so clearly this term has to do with the transformation rule, with the part of the transformation rule that has to do with the density part. Now this term is universal, so if I consider the covariant derivative of a contravariant tensor density, now I first have the terms corresponding, the standard terms corresponding to the derivative of a standard contravariant tensor, in this case a contravariant vector, and then a term just like this, P nu, and the same for any other tensor. There is always a term like this that multiplies the tensor. You can check that this works well for the determinant of the metric. The metric is covariantly constant for the Levi-Civita connection. This means that the covariant derivative vanishes. You would expect that the covariant derivative of the determinant of the metric also vanishes. But if you don't take into account this additional term, you will not be able to prove that, because if you deal with g as if it is just a scalar, this would be the partial derivative of the determinant of the metric. Clearly, in general, this is different from 0. However, there is a term minus the weight of the determinant of the metric. We said that it was 2, so there is a mu rho, and then g. Now let's expand this. The first term is the same, then minus 2, and if I operate here, I can do this in this way. This would be just partial mu g and this factor of 1/2, and then g, this g here, these two g's cancel, the factors of 2 cancel, and then this gives me identically 0, as you expect. So this term is fundamental, and it is important to remember that G is a tensor density and not just a tensor. A more interesting tensor density is the Levi-Civita symbol. We have already studied it in the case of special relativity, so just for the Minkowski metric. But in presence of a general metric, it behaves well. The definition is a bit more complicated, and really you can show that it is a tensor density and not just a tensor of weight omega equal to +1. So let us see how it works. Remember that the main property that we want of this Levi-Civita symbol is that when we take all the components, the different components in this order, which defines an orientation, so by definition this will be +1, and that this should be the same in any coordinate system. So this property that the components are +1 should remain true when I change coordinates. So let us see how I do it, or let us prove that by considering that it is a tensor density of weight +1, this property really remains true. The only caveat that I will have is that I'm going to consider transformations that do not change the orientation. And this means that the determinant of the Jacobian is positive. So before I prove this, let me remind you that if I have a matrix, a square matrix, let me write it like this, with its components mu and nu, then the determinant of the matrix, with if this is defined to be +1, can be computed in this way. So I just multiply all these components, I contract them with the Levi-Civita symbol. For instance, the first term that you get if you do this has all the mu1 up to mu d equal to 0 and d minus 1, which gives you factor 1, and this is the product of all the terms in the diagonal, which is if you want, is the first or the simplest term in the computation of the determinant, and you get the rest. Okay. So now consider what is the value of the component 0, not 1, but d minus 1 in the primed coordinate system. And if it is, well, first there are all these Jacobian, let's use Jacobians, okay, it's just a bit simpler. All these Jacobian factors, mu 1, d minus 1, mu d epsilon, mu 1 up to mu d, this by definition. Okay, we usually write the transformation of with all the indices alpha 1 to alpha d, and here we write alpha 1 alpha d, but we are just evaluating this for the particular case in which alpha 1 is 0 and so on, and alpha d is d minus 1. Okay, and this is just what I have written here, and you already see the emergence of the determinant. But then, if this is a tensor density of weight omega equal to +1, there is a factor of the determinant of the Jacobian raised to the power minus omega, and omega is 1, so this is d minus 1. But this is just the determinant of the Jacobian. Okay, not the absolute value, but so what you get is that this is +1. Okay, so just only if you consider that this is a tensor density of weight 1, this property that the component 0, 1 up to d minus 1 of the Levi-Civita symbol is always +1 in all coordinate systems remains true. Since the rest of the components are defined by permutations of this component 0, 1 to d minus 1, all the components are constant, and they have the value of +1, -1, or 0 if some indices are repeated. But as you know, it is not the same to be constant that to be covariantly constant. To be covariantly constant means that the covariant derivative has to be 0, and probably you want this property to be satisfied. Okay. So let's see that this indeed is satisfied if we deal with epsilon as a tensor density. If it is a tensor density, this means that first there is this term and all the terms that correspond to the covariant derivative of a standard tensor. So mu, nu1, rho, epsilon, rho, nu2 up to nu d, plus, and so on. Okay, and the last term could be minus omega mu rho epsilon nu1 to nu d. Okay, so now let's compute this. This is 0 because epsilon is constant, and let me write all these d terms in this way. This is just -1. Let me show you that this is I'll show you that this is true, times d, and mu rho nu1 epsilon nu2 up to nu d, and then rho minus, okay, I should have replaced omega with 1, so this is just a minus mu rho epsilon nu1 up to nu d. Let me show you that this thing that I have written here is the same that I have up there also in brackets. Okay. You see that the difference between this and this is basically that in all the terms, instead of the natural order with rho first and so on, I have moved rho to the last position. In this case, this means that I make d minus 1 permutations to bring rho to the last position, so I get a factor of -1 to the d minus 1, and indeed this should be d minus 1. Okay, so good that I checked. And the rest of the terms have essentially the same structure. The next one, to bring the row in the next term from the second position to the last one, I have to do d minus 2 permutations, so I get that factor, but this is taken into account here. Okay, just please check that this is correct. Let me expand this. So because I have this d, okay, I can expand this in this way. So this would be mu rho mu 1 to new d rho and then cyclic permutations with the corresponding index. Okay, that depends on the particular number of the particular dimension in which we are working. But for instance, I can put it also in this way. So this will be minus mu rho. I interchange mu 1 and mu 2. Epsilon mu 1, then mu 3, and then mu d and rho. But if I move this to this place, okay, I get a factor minus, and this would be minus 1 to the d minus 2. With this minus, it would be plus and d minus 2, which is exactly what you will have there. And so on. You just do the same and find all the terms that you have here, that all of them are reproduced here. Okay. So let me just clean this up. Okay. Okay, the last thing that you need to know is that this is minus 1. You can write this in this final way. D plus 1 omega mu rho, and then mu 1 epsilon mu 2 mu d and rho. Okay, so you include the rho in this, and this takes care of the last term. Well, how do I see that this is actually what you have up there? Okay, I would expand all these d plus 1 terms, and the first d of them will be just this. This is the easy part to see. But the last part is to see that, well, the only term which is not included here is the term in which rho is in gamma. Okay, and that, well, you just have to check that the sign is correct and so on. Think about it, and if you don't see it, we will do an exercise about it, and I will do this calculation in full gory detail. The important part is that, well, here we are antisymmetrizing d plus 1 terms in d dimensions, and this is automatically 0. There is not a much better way of seeing that this is 0. Okay, and this is something that this kind of proof in which you show that something is equal to the antisymmetrization of more than d indices. It's used quite often. Sometimes you can obtain identities by antisymmetrizing more than the indices and then expanding the result, and then you find the relations between things with less indices antisymmetrized. Okay, so we proved that this epsilon is not just covariant, but it's not just constant, but it's also covariantly constant. And this reflects the idea that the values, the components of epsilon are constant, but they are constant even after I change coordinates. Now, observe, and this is important, that if I have any object which has d indices, okay, it will always be proportional to epsilon, to the Levi-Civita symbol. Well, how do I see this? Well, I have to realize that if A is antisymmetric, so I am assuming that this is antisymmetric in all the indices, otherwise what I said doesn't make any sense. So assuming that this is completely antisymmetric means that the only component which is different from 0 and independent is this one. Okay, so 1, 2, and so on, because there are two repeated indices, blah blah blah, just like epsilon. This means that I only need to determine one component. The rest of the components are either 0 because there are repeated indices, or they have the same value up to a sign that depends on the permutation of the indices that I need to do to reach that particular order. So there will be some number, okay, and well, you multiply it by 1 or minus 1, just as this epsilon. So I need to find this coefficient A if I want to write it this way. How do I do this? Okay, it is convenient to define epsilon mu1 mu d as the tensor density that you obtain by lowering indices with the metric. This is a tensor density. These are tensor densities of weight 0, or just tensors. This means that this is a tensor density of weight 1. What is the value of anything which is completely antisymmetric? Is only has one independent component. So what is the independent component of what is the value of the independent component of epsilon with indices down? So let me compute this one. And you see that, well, this is G0, nu 1, blah, blah, G, D minus 1, nu D, epsilon nu 1, nu D, and automatically this is the definition of the determinant of the metric. Okay, so this is the value. In our conventions, the determinant of G is negative in 4 dimensions. This means that epsilon 0, 1, d minus 1 is minus the absolute value of the determinant of G, which is what sometimes I write as this. Okay, just this is to emphasize that it is negative. Okay, I need also a lot of identities that tell me what is the result of the contraction of epsilon with indices up and epsilon with indices down. We have done this for the three-dimensional epsilon symbol in flat space, which we denote by epsilon ijk. So in that case there was no difference between indices up and indices down, but here there is such a difference. The contraction that I will explain now is the total contraction. We can study what happens with when you contract less indices. And here you see that, well, only the components which are different from 0 matter. How many there are? Well, if I start with 0, 1 up to d minus 1 and permutation, so there are d factorial different terms, and each of them, and the first of them is 0 blah 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 and 0 blah blah blah, which gives me minus g. But then I have d factorial terms like this, because every time I make a permutation here, I also make a permutation here, the same permutation, and well, they always add up. So this is d minus d factorial absolute value of g, or if you want, minus d factorial g, as you want. Okay, this is the other thing that I need to know. Now, knowing this property, I will tell you what happens with other contractions. I can come here, okay, and multiply both terms by epsilon mu1 up to mu d. But this I know what it gives me because I just computed it. So this is minus, sorry, a, and then, sorry, d factorial g. So this is how I find this factor a. By contracting with epsilon with the indices down. Okay. So having this formula, knowing this mechanism for finding this coefficient and knowing this property, I could come here, okay, and instead of applying this result, okay, seeing that everything is proportional to something with d plus 1 indices antisymmetrized, I can do the following. I can multiply this both sides by epsilon with the indices down. Sorry, let me explain it in a different way. I would take minus 1 to the d minus 1 times d omega mu rho epsilon nu mu2 mu d rho minus, on the second term, mu rho epsilon nu 1 nu d. I know that this is proportional to epsilon nu 1 nu d because it has all indices, d antisymmetrized indices. So this has to be proportional to epsilon nu 1 to nu d. And I want to find the coefficient, let me call it b. So I apply this result basically, and I multiply both terms by epsilon nu 1 nu d. Okay, since I am multiplying by epsilon nu 1 nu d, I can remove this antisymmetrization because these two things are contracted, and then I get minus 1 d minus 1 times d gamma mu rho nu 1 epsilon nu 1 nu 2 up to nu d epsilon, and let me move this rho to the first position, which gives me a factor of minus 1 to the d minus 1 to cancel this one, and then I have rho nu 2 up to nu d. Then the second term is minus mu rho and is epsilon times epsilon, which is d factorial g, and then the last term is b d factorial g. Okay, we're almost there. The only thing that we need to know is what is this. So now we go, and I have to explain you how to compute contractions, incomplete contractions of two epsilon symbols. This is very similar to the three-dimensional case. So this is going to be proportional to g nu 1 rho. Only when nu is equal to rho, this can be different from 0, because nu 2 up to nu d have to be equal. Okay, this means that rho has to be different from the rest, and nu has to be also different from the rest. So it is the other one. It is the index which is not nu 2 up to nu d. In other words, rho is equal to nu 1. What is the factor? Instead of d factorial contractions, here we have d minus 1 factorial contractions. This is proportional to g, so this is the result. Okay, now let's multiply here. I have d times d minus 1 factorial, so I have d factorial gamma mu rho, and now nu 1 is transformed into rho times g minus mu rho d factorial g equal to b d factorial g, but you see that this term and this term cancel and b is equal to 0. This is an alternative way of seeing it. And now that we are at it, I can give you the general formula for these contractions. It goes like this. So suppose that I only contract d minus n. Okay, let me call it something else. An epsilon beta 1 beta n mu 1 mu d minus n. Okay, the result of this general contraction is this object that I am going to define now. Then there is a factor of d minus n factorial, as you can expect. There is also a factor of n factorial, which is related to the definition of this object. Okay. And there is a factor of g. So this would be the general result. Now let me define what this g is. Okay, and g alpha 1 alpha n beta 1 beta n is the antisymmetrized product of these matrices. These are deltas, remember, written in some funny way, but it would be the same as writing delta. Okay, this is n. Okay, this is antisymmetrized in alpha and n, and you can check that this is the same as if I antisymmetrize in betas. Okay, so this symbol is completely antisymmetric in all alphas and all betas. This is a definition. I think I gave this definition in the Minkowski case. So it is exactly the same, because g and I could replace this by eta or by delta. And here it is the same result, except for the presence of this g, which was just minus 1 in the Lorentzian case, when in the Minkowski case, sorry, because this is Lorentzian. This is the general formula. We have applied it here with only one free uncontracted index to prove that this is 0. I have shown you that you get exactly the same result that with the reasoning that I advanced. That okay, it is more difficult to see for you probably, but it is due to the same, and it is correct, which is more important. Okay, and we have proven that the epsilon symbol is covariant and constant and covariantly constant. You can also prove that with the indices down, this is also covariantly constant, although it is not constant anymore, because we have said that the non-vanishing components are proportional to the determinant of the metric. I suggest that if you want to do some exercise with these indices, you try to apply the general formula for a tensor, for the covariant derivative of a tensor density of epsilon, taking into account that the weight is +1. You will probably have to do similar gymnastics, okay? And you will also have to use the fact that in this case it is not the partial derivative of epsilon mu is not 0, because it is not a constant anymore, it is the determinant of the metric, but that the covariant derivative in the sense of tensor density of this will be 0. Okay, just the result that we proved at the beginning. Another possibility is that you use that this is d factorial g, and if you take the covariant derivative, which satisfies the Leibniz rule, this gives you this, which we have shown is 0. Here this is a tensor density of weight 1, another tensor density of weight 1, and remember that g is a tensor density of weight 2, so everything works. Using the covariant derivative defined on tensor densities, this is completely consistent. And now that this is 0, you have this property, and you have the other property that we already proved. Mu1 to mu d, this is 0. So what you prove is that this is equal to 0. And since this is whatever, because it has to have, has to be the result of this, has to be completely antisymmetric in the indices mu1 to mu d, it will be proportional to mu1 to mu d. So this is some a or some number, maybe call it c, times epsilon mu1 to mu d, contracted with mu1 to mu d, and you get 0, means that c is 0, and that this covariant derivative is 0. This is an alternative way, a bit cheap if you want, but you get the same. If you want to do some more exercise, you should try to prove this property using directly the definition of the covariant derivative of epsilon. Remember that in the special relativity case, that is the Minkowski metric, we use the Levi-Civita symbol to construct the Poincaré invariant volume element for integration. We defined t for x as 1/4 factorial with a minus sign that corresponded to the determinant, or the sign of the determinant of the metric, epsilon mu nu, rho sigma in this case. So this is mu up to the x sigma. And clearly now, since epsilon takes a different value, it is not plus or minus 1 anymore. In presence of a non-trivial metric, epsilon takes the, with the indices down, takes the values g or minus g, where g is the determinant of the metric. It is clear that we have to modify this definition. Also, Poincaré invariance is not relevant anymore. What we want is full invariance under general coordinate transformations. So what we are going to do now is to see how to use this epsilon symbol that we have just defined with all the properties that we have defined to construct a general coordinate transformation invariant, or the diffeomorphism invariant volume element in d dimensions. Let me first generalize this definition of the volume element to d dimensions. Because what we are going to do is to check where it fails to be invariant and see how we can fix it. Instead of minus 1, in general you have minus 1 to the minus 1, because this is the sign of the determinant of the metric. You can write also sign of g if you prefer. Then 4 factorial will become d factorial, epsilon will become epsilon mu1 to mu d, and this will become epsilon dx mu1 to dx mu d. We want to see how this transforms, so let me write now this would be in the transformed coordinates. This is epsilon prime, and these are the coordinates, the transformed coordinates y. And now I apply the definition. This is still the sign of g. And I don't need to look much further, because I know that this is tensor density of weight 1. And if it wasn't because of this tensor, the fact that it is a tensor density, then we would have this dy is a blah blah blah. This could transform as a covariant tensor, fully antisymmetric of d components, which is invariant. So up to the factor that comes, because it is a tensor density of weight 1, and this is just j minus 1, the determinant of j minus 1, the rest is just invariant. Okay, so in order to construct something which is completely invariant, I need to cancel this, which means that I need to multiply by a density, now a scalar density, because I don't have more free indices to play with, of weight. If I want to multiply, it has to be with weight minus 1, or divide by a scalar density of weight 1, which would be a square root of g. So the thing that I now will replace dy, okay, now this notation is really not correct anymore. My volume element, which is invariant, will be this one. So I divide by the square root of g, or better, I is sine of g d factorial square root of g, because this expression is invariant under general coordinate transformations, and this I can call dv or whatever, to indicate that this is the d-dimensional volume element. I have to check, I have to see if I recover the Minkowski result. This is more or less obvious, because in Minkowski this becomes 1, so this factor disappears. I really recover what I was using. And another thing that I want to see is what happens if I express this in coordinates in a less covariant way. Okay, so let me expand this. This is just the sine of g d factorial square root of g, and I know that this has only one independent component. Okay, and I get d factorial terms which always add up, because any permutation of this corresponds to any permutation, to the same permutation of that. So this would be epsilon 0 up to d minus 1 dx0 dx d minus 1. I know with a factor of d factorial that cancels this one, and I know that this is just g, okay, which is sine of g if you want, and the absolute value of the determinant of g. Now this sine will cancel this one, and I have this divided by the square root, so this is equivalent to the square root of g dx0 dx d minus 1, which is what typically we write in this form, d dx. So the invariant volume, d-dimensional volume element in coordinates like this is always written in this way. The difference with the Minkowski case is this factor of a square root of g. If you deal with this in a pedestrian way, you will see that this d dx, which is just this piece, transforms with a factor of the which is the determinant of the Jacobian of the transformation, which is exactly the opposite to that of this scalar density. So this whole thing is invariant no matter how you do it. The moral is that if I want to make an integral over some d-dimensional volume, okay, this is what I have to take into account. Suppose that I am integrating over a three-dimensional space written in is just with the Euclidean metric, but in spherical coordinates. So this would be a three-dimensional integral. The coordinates are the r, the theta, the phi. Okay, the orientation just gives me a sign. And this square root of g is the determinant of a metric that, as we computed before, is 1 r squared sine squared of theta. Okay, now if I multiply, I get r fourth sine squared of theta. So this is just, after I take the square root, r squared sine theta. And this is, well, the form of the integral, the volume integral in spherical coordinates, as you already know, r squared sine theta. One important thing to always check is that the dimensions are right. So if the metric has dimensions of length squared, which is what we have always assuming, this is okay if r has dimensions of length, but then this has dimensions of length squared, which means that the angles are dimensional. Of course, sines or cosines are always i-dimensional, and phi must be also i-dimensional. So this has dimensions of length, and length squared dimensions of length cube, right? Which is the right result to start with. And okay, finally, so if you, for instance, you just want to integrate this over from 0 to r, okay, you just do this in pieces. You know that you have to integrate the r squared. Maybe this is the integrals are separated from 0 to r. Theta goes from 0 to pi, and this is theta sine theta, and phi goes from 0 to 2 pi. This integral gives me 2 pi. This is the integral of minus the cosine, so it is minus cosine theta between pi and 0, which gives me cosine minus cosine of pi is minus 1, so this gives me plus 1, and minus plus, so this gives me 2. Okay, and so this is 4 pi, which is the solid angle, and this integral in r is, as you know, is 1/3 of r cubed evaluated between r and 0. So it's just 4/3 pi r cubed, as you expect. Okay, but we would never have obtained this result if we have not taken into account this square root of g. Okay, of course there are more pedestrian ways of generating more or less the same result. In this case, if you had started with dx, dy, dz, and you perform the change of coordinates, is fine, because you start with a metric whose determinant is just 1, the Euclidean metric. Okay, so you don't include it there from the beginning, but you can have first, you may not have a metric with a square determinant equal to g to relate your metric to. Okay, here this metric is related to this one, to the 1 Euclidean metric, but your metric may not be related to that. So you always have to take into account this factor of square root of g. And this is it. I think this is more or less all the differential geometry that you need to survive in this course. If something else arises, we will explain it along the way.